Okay, good afternoon, all of you. Again, welcome to all participant and our speaker and today's second session. Dr. Rai, sir. Sir, ready, sir?
Hello. Yes, sir, I'm ready.
Okay, thank you, sir. So I would like to invite Dr. Dibya Prakash Rai, sir. Okay, sir, please.
Good afternoon, everyone. I'm extremely sorry for this technical problem that I had to shift from one computer to another to solve this problem. And finally, it has done. I think you can see my slides. Is it clear?
Yes, sir.
Okay. So we had a series of lectures, and this the whole day. But during my time, I had to face, and you all had to face some problems. Extremely sorry for that. So, and so today I'm going to talk about transition metal-based Heusler alloys and its properties. My name is Dr. Dibya Prakash Rai. I'm an assistant professor in the Department of Physics, Pachhunga University College, Mizoram University campus. And uh, uh, so many people doesn't have much idea about the northeastern part, and northeast is a very beautiful place. It's very cool and less populated, but the picture doesn't look that it is less crowded. This is the Aizawl city where I'm currently stationed and where I'm working. So this is the college. The downside, the upper picture shows the crowded buildings of the Aizawl city, and the green color buildings in the picture is our college campus. That is Pachhunga University College, campus of Mizoram University, and this college in the capital city of Mizoram, that is called Aizawl. The population is around 10 lakhs, almost equivalent to one district of UP or Bihar. And the area is 21,000 square kilometer, and the climatic condition is very pleasant here. The summer temperature range from 20 to 30, and winter is 7 to 20. It's neither very cold nor very hot, and we are connected with the airport. We have one airport, but we don't have railways out here because it is a hilly state. So because of that, we don't have railway. The nearest railway is Silchar, that is Assam, and Aizawl can be easily traveled from Guwahati, that is the biggest city in the northeastern India. And so this is the outline of my lecture. So introduction. In introductions, I will discuss about the chronology of the development of Heusler alloys, then the types of Heusler alloys, and the methodology or the tools that we have used for studying the various properties of the Heusler alloys, and some of the properties of Heusler alloys like electronic properties, magnetic properties, and thermoelectric properties of Heusler alloys. So the first this Heusler compound was first discovered in 1903 by a German chemist named Friedrich Heusler, and this compound name, is the name of the compound itself is now called a Heusler compound, after the name of the person who has discovered this compound. And this is an intermetallic compound, which is constituents of copper, manganese, and aluminum. Okay, the constituent, the weight percentage of the constituent elements are 2 part of copper, 1 part of manganese, and 1 part of aluminum. And the overall compound, the property of the overall compound is a ferromagnetic compound. So the prototype compound looks like Cu2MnAl, Okay, so Cu2MnAl is a ferromagnet, although none of its constituent element is non-magnetic by itself. So in 1934, Bradley and Rogers has actually found out the structure of the Heusler compound, and they have found the Heusler compound, that is Cu2MnAl, crystallizes in FCC structure having the FM3M space group, okay, and the classification number 225. And in the same year, 1934, the son Heusler, okay, the son of the first Heusler, that is Friedrich Heusler, whose name was O. Heusler. The son of the Friedrich Heusler was O. Heusler. I don't know the first full name. He has found another compounds with the same combinations. In the same constituents of transition metals and the main group elements. He found that the space group was different. It was a FCC structure, but the space group was different. The space group was F43M, and classification number was 216, and which people used to call that Heusler compound as inverse or inverted Heusler compounds. Heusler compounds can be described as an interconnection between the rock salt and zinc blade lattices, or as four interpenetrating space sublattices, of which two are formed from the same element. So here, this is the rock salt structure having the binary atoms Y and Z type, and this is the zinc blend, and this is X and Z type. So you can see the green is Z element, and this brown is Y element, and X is the this blue is the X element. So if you mix up this, two compounds like rock salt and the zinc blend, then we will get another type of structure. So this structure is actually a Heusler type of structure. So you can have the four interpenetrating FCC sublattices are there. This is X. This is given by X. Blue. This blue color atom is represented by X. So this is the four interpenetrating sublattices. So in 1951, and 52, Notny and Jua has published a result on a different group of materials named namely LiMgAs, that is Notny structure, and the CuMgAs, that is Jua structures. Okay, nowadays those structures are called Notny and Jua phases. The concept of this connection between Notny Jua phases was established by L. Castells. So the Notny and Jua phases has been combined together to get the new structure, and that was something like the previous one, which is equivalent to the half Heusler compound, half Heusler alloy. So the half Heusler alloy and the type of this half Heusler for the time being, just remember the name. So we will talk in the next slide. So Heusler alloy with this combined phases are called half Heusler, which one of the four FCC sublattices of the full Heusler is empty. By filling the fourth sublattices, a series of compound can be formed between half and full Heuslers, which we can describe as XYZ and X2YZ respectively. XY are the transition metal elements, and Z is the main group elements. So the full Heusler compounds have other variants too, including the inverse structure, and the inverse structures is formed when the X and the Y will swap their positions. And another one is quaternary. Quaternary means you will have four distinct atoms in the compound. So in 1976, Giebeck and Webster reported ferromagnetic properties of Fe2MnSi. So this is also another type of full Heusler alloys, and the Curie temperature of 21 K, and R.A.D. Groot et al. This is the one of the breakthrough in the Heusler alloys, because they have produced found out a very peculiar properties that is called a half metallic property of NiMnSb from first principle calculations. Then Ford and group gave an idea about the implementation of half metallic behavior in spintronics. Then after that, the rigorous research attention was drawn toward the half Heusler compounds. So Aizawl first reported the half metallic behavior in CO2Y type full Heusler compounds. Then S.A. Wolf has given a future prospectus of the spintronics in his paper. This is the type of Heusler alloys. So you have two types of Heusler alloys. So the first one is the half Heusler alloys. So you can see out here. So the red balls are transition metals, but you can see that just beside the red ball there is some empty ball that is denoted by some dotted lines. Some dotted lines are there. So so that means this is the empty space. So this empty space. So in this this compound you have only 4 interpenetrating FCC lattices that is given by red balls, but the which is given by the dotted circle is the empty one. So this is the half Heusler compound which crystallizes in FCC structures having the space group F43M. Now if this dotted circle has been filled up by another transition element, then we will get this one, the left side, we will get this side. So you can see the 2 red balls, solid balls here there in the 4 FCC interpenetrating lattices has been now filled up by the 2 solid balls. Those are the transition elements. So here this is called the regular Heusler alloys because they crystallize in FCC structures having, but their space group is FM3M. So another one is, now if this, so you can say this red ball is the X element. So we have 2 red balls, or you can say 2 X elements in the interpenetrating FCC lattices. So we can say this is X2YZ type structure. So now if this element is swapped with the blue element, blue is also transition element. If the blue and the red element has been swapped, then we will get this kind of structure. This is the inverse Heusler alloys which crystallizes in FCC structures, but the space group will be different, that is F43M. So here is the how the this thing half Heusler alloys looks like. This is the zinc blende structures, and I have already said when the zinc blende and rock salts are combined together, you will get this kind of Heusler alloys. You can see the blue balls, dotted balls in the 4 interpenetrating lattice has been occupied by the 4 4 atoms. So the space group is 4F3M, and the classification number is 216, and the position is X is half, 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 Y is 1/4, 1/4, 1/4, and Z is 0, 0, 0, and the 3/4 position is empty. If this 3/4 position has been occupied by some of the transition element, then that compound will become a full Heusler alloys. So what is X and what is Y out here? The X and Y are basically, they are transition metal based transition metals, okay, which is have the d orbitals. So this is X and Y are in the, like here in the transition metal groups. And Z is the main group. We used to call it the main group, and generally they have the p orbitals, or we can also say p block elements are there. And the full Heusler alloys is 2:1:1. So the stoichiometric ratio of the full Heusler alloys is 2:1:1, and that is the prototype structure of full Heusler alloy is Cu2MnL that has been first discovered by Friedrich Heusler. Okay, and here X2YZ, here the same thing. X and Y are always the transition metal, and Z is always the p block elements. So this is the prototype Heusler full Heusler alloys which crystallizes in FCC structures having the space group FM3M. And the full Heusler alloys are also of 2 types. One I have already discussed about the Cu2MnL type. Another one is Hg2CuTi type. Okay, so in Cu2 MNAL type, you can see that CO2 FeAl is an example of this CO2 MNAL type full Heusler alloys, which has the FM3M type of space group, and Fe2COL is the Hg2CuTi type structure. So we used to call them XA type, or we can also call them inverse Heusler alloys. And the first one is is called the direct or the regular one. And some people used to call them direct full Heusler alloy, and some people used to call them that regular full Heusler alloys, which has the Cu2 MNL type structure. Why this is the regular and why this is the inverse is because CO is in the X position, so this is X2 YZ type. So here the electronegativity of the CO element is bigger than the Fe. So mostly in the direct full Heusler type, the electronegativity of the X element is bigger than the Y element. Here just the opposite. Okay, so electronegativity of Fe is less than the CO. So but X2Y, this X2 position has been occupied by Fe. So this is, we just name them as inverse Heusler alloys. And another type of Heusler alloys, this is also a full Heusler alloys because all the sublattice has been occupied by the atoms. So but though no two atoms, same atoms are repeating out here, all the atoms are all different. So NBRHCrAl is an example, which has the stoichiometric ratio of 1:1:1. So all the atoms are different here. So this is also a full Heusler alloys. This is also a full Heusler alloy, so, because all the sublattice has been occupied. So some of the properties of the Heusler alloys are magnetic properties, very interesting magnetic properties, electronic properties, and thermoelectric properties, and shape memory alloys. So to study the different properties of the Heusler alloys, we have opted a tool or the method that is called density functional theory. Density functional theory is widely used quantum mechanical tools that study properties of solid state materials, and it provides us the underlying phenomena depending upon the single potential model. It offers a powerful and elegant way for calculating the ground state properties of interacting electrons. It is efficiently used for calculating the band structures of the solid in physics and binding energy of molecules in chemistry. It has been extensively used for a single atom to a complex system, ranging from the protein to any other compounds, okay, periodic system. So it has been remarkably successful in explaining the magnetic properties of transition metals and their alloys as well. So why we are using DFT is because there is a certain limitations of the quantum mechanical tools like Schrodinger equations. So many body systems cannot be solved by the Schrodinger equation. Schrodinger equations are limited to hydrogen-like elements, the hydrogen-like systems where the number of electrons or the interacting entities are less. So so if you have a carbon, this I have taken from some presentation. So if you have a carbon dioxide molecules, and if you have to solve the carbon dioxide molecules, that means you have to find out the ground state energy of the carbon molecules. That means so there are around 22 electrons. So this 22 electrons has to be, like it will have three degrees of freedom for its interactions. So 3 degrees of freedoms in its interactions. So totals you have 66. So 66 interactions you have to consider. So to deal with all this might be not tough, but if you increase the number of atoms, so the dimension will become 2300. So this is the 100 atom nanoclusters. If you have to take interactions and you have to develop the potential for that analytical way, that is very, very difficult. So so that is the limitation of the Schrodinger equation. So we have to opt for another type of quantum mechanical tool that is called the density functional theory. So what is the nice thing about density functional theory? This picture I have taken from the quantum espresso slides. Somebody has already presented it. So so nice thing about DFT is an ab initio, no empirical informations, and predictive power, very accurate for most of the materials. It can calculate lots of properties, and for developing this theory, Walter Cohen has received a Nobel Prize in 1998 as well. So the theory is based on the Hoenberg and Cohen theorem. This Hoenberg and Cohen theorem is divided into two parts. The first theorem says that the ground state energy of Schrodinger equation is a unique functional of electron density. So if the two systems of electrons trapped in a potential V1 and V2 and have the same ground state, this is the NR electron density, then V1 and the other V1 is necessarily a constant. So V1 minus V is necessarily a constant. So this theorem says that the ground state energy is a unique functional of electron density. But which electron density, that we do not know. So the second theorem talks about the density, electron density, that particular density which minimizes the energy of all functional is the true electron density of that particular system corresponding to the full ground state solution. So from the variation principle, it has been proved that there is the electron density, a unique electron density, which will minimize the energy of the systems, or which will give you the ground state energy of the particular system. So details has already been discussed by the some of the professors in their preceding talks. So I will not go in details. And so by considering the energy as a unique functional of the electron density, a Quant Sum Schrodinger equation, a many-body Schrodinger many-body electron system has been reduced to a single body problem now, which is given by the Quant Sum equation. So out here is the Quant Sum equation. So you can see here, this is the energy, and this is the your external potential. This is your Hartree potential, and this is your exchange potential is here, and this is the eigenvalue and the eigenfunctions. So these equations will be solved by what you call self-consistent method, because to calculate the psi, to know the the result of this equations, we need to know the psi. Okay, and for that potential has to be developed, and to know and within that potential, because potential itself is the functional of electron density, so within that potential you have the electron density. So that electron density you have to the electron density has to be solved, and for that what we have to do is we have to take the trial electron density, and once the trial electron density is supplied to the equations, then it will be solved by the so there are different computational codes to solve that problem. So the algorithm is something look like this. So you have to guess this one. This is the trial electron density. Then because of this trial density, we have the potential. We have to develop the potential, and with that potential, there will be a Hamiltonian, that is the Quant Sum equation. If we fit into the Quant Sum equation, and this Quant Sum equation will be solved self-consistently, and you will get another new type of electron density. If this electron density is giving you the minimum energy, then this is the true electron density for that particular system. If not, then again it will go follow this cycle. So that is called the self-consistent type of calculations. So so here in Quant Sum equations, other than these two types of potential, the effective potential and the Hartree type of potential, we have some other type of potential is also added, that is called the exchange correlation potential. This exchange correlation potential will include all the quantum mechanical interaction part. So the main results will depends upon the this thing, exchange correlation potential, which includes all the quantum mechanical effect. So there are and those that is very unknown. That is, we do not know the perfect picture of that particular exchange correlation. So there are plenty of approximations regarding that potential. Exchange correlation potential, and the first type of exchange correlation potential is LDA, which depends upon the electron density, and another one which is depends upon the shape of the electron density. Another one is the generalized gradient approximation, so that relies on the electron density as well as the gradient of the electron density. That sometimes we used to call this is the first order corrections. And another one is meta GGA. Which includes all this electron density plus the second order corrections, and the another one is hyper GGA, and this is the last one is generalized RPA. There are more to be, I think, discovered. So till now we are much familiar with all these 5 types of these things. Exchange correlation potentials. So if you climb up the ladder, the efficiency or the perfection of these functionals will increase. That means the results will be better if you climb the ladder in the upward directions. But if you climb down the ladder, what will happen is the functional looks more easy. That means it will ease your computational cost, but you have to compromise with the result. So that's why this is given by the what do you call Jacob ladder. This is called the Jacobian ladder. So I have not much idea about the hyper GGA and generalized RPA, but in our court we have GGA, meta GGA, and LSTA. So all this DFT has been programmed in our code that belongs to my supervisor, Professor R.K. Thapa. It is a licensed code. We call it Win2K. I think it's a very versatile code, and it is good for transition metal-based compounds. So why we are choosing the Heusler alloys is because of its room temperature fabrications. Another reason is the stability. It is very stable compounds, and the structure is very easy. That is FCC type structures. Another one is its electronic and magnetic properties are predictive. We can easily estimate the electronic and magnetic properties of these compounds before going for any rigorous calculations. So so that electronic and magnetic properties relies on Slater-Pauling rule, which is discussed in this paper. In this Slater-Pauling rule says that for 2 types of Heusler compounds, that is full Heuslers and the half Heuslers, the 2 rules are there. So MT is equal to ZT minus 18, that is XYZ type compound, that is the half Heuslers, and MT is equal to ZT minus 24, and this will give you X2YZ type of structure. Okay, so MT is the total magnetic moment, and ZT is the total valence electrons of that particular compound. So same out here also. This is MT is the total magnetic moment, and ZT is the total magnetic moment. So now here, this is just the example. So if you take XCOSB, this is the XYZ type. This is the half Heusler compound. So Ti is 4. There are 4 valence electrons in Ti, and in CO there are 9 valence electrons, and SB there are 5 valence electrons. So the total valence electron, that is ZT, will be equal to 18. So 18 minus 18 will be 0. So according to this rule, so we can pre-assume this compound, the properties of this compound. This is a non-magnetic. This should be non-magnetic, and it should have a semiconducting band gap. So because your total magnetic moment is 0. Another one is V. So we are going towards the right side of the right-hand side of the periodic table in the transition metal elements. So B is your 5. 5 means the total number of valence electrons. So 5 plus 9 plus 5 is 19. So if you put this 19, that is ZT, total number of valence electrons. Here ZT 19 minus 18 will be 1. So you have some finite value of magnetic moment. So this proves that this is a magnetic system, okay, having the magnetic moment 1. and it has a band gap too on the spin down channel, but the spin up channel doesn't have a band gap. So and the other one is this one, chromium. Okay, so CrCOSB, in CrCOSB you have 6, 9 and 5, that is 20. 20 minus 18 will give you 2. So that also gives you the finite value of magnetic moment. So this is also a magnetic system, so and so on like this. But and at the same times there is a band gap here for the first compound and the second compound, third compound and the fourth compound. In the first compounds we have the band gap in both the sides, so both the spin up and spin down channel. So this is a semiconductor, but here only in one type, I mean the one channel you have the band gap, other is the conducting. Spin up is the conducting, here spin up is the conducting, and this is the semiconducting. So this semiconducting and the conducting behavior of this ferromagnetic systems is called half metal property. And how this has been formed is because of the DD hybridization. You have X CO, CO, and this X is Ti also D, and CO also D. So there will be a DD hybridization of this one. So when the DD orbital will hybridize, then this is a bonding state. So bonding state will be completely filled up. So you have 3 T2Z and 2 EZ bands there. So so altogether there are 10 electrons in the d orbitals. So the d orbitals has been completely filled up. So this has been in the spin down. Sorry, this is in the Fermi level, and the empty bands, empty, which is denoted by the anti-bonding states. So these anti-bonding states are vacant. This level will go above this one. So 10 and 8 will give you 18. So 18 will give you 18 minus 18 will give you 0. The 8 electrons is coming from the sp orbital. Okay, so S and P together will give you 8, which is completely filled up. That is also in this below the Fermi level. So 8 and this will give you the 18. So 18 minus 18 is 0. So this is the predictive result. This is not the actual result or the experimental or the theoretical result. This is the predictive result, okay, based on the Slater-Pauling rule. So according to the Slater-Pauling rules, the magnetic moment should be changed like this. Okay, so with the increase of the your ZT, that is the valence electrons, your magnetic moment will keep on changing like this. If you have 18 valence electrons, if your compound is 18 COTISB, this will give you 0. This would be non-magnetic and semiconductor. But here all this will give you the finite value of the magnetic moment. So this would be a ferromagnet with the ferromagnet with the band gap in the spin down channel. So similarly for full Heusler alloys, we will have this MT is equal to ZT minus 24. Okay, MZT minus 24. So this rule will be applied. So the magnetic moment is easily predictive. So so this is the example of X2YZ type. This is CO2 MnSi. So this is the structure of CO2 Mn. Sorry, this is the like the bonding structure of CO2 MnSi. So you can see out here first COD and COD will be hybridized. This hybridize like the orbitals will now again hybridize with the MnD orbitals, which is not the hybrid one. So there will be this CO hybridization will take place. Then after that, this CO hybridization will hybridize with the MnD orbitals. So this will give you the same pictures will be here. This will give you the T2Z and EZ. This is the completely filled up, and this is not the empty bands. So this is the above the Fermi level, and this is the one. So because of this this is completely filled up, and this is incomplete. Sorry, it is incompletely filled. So this is in the below above the Fermi level, and this is the below the Fermi level. So this is the gap. So see out here, but you can see this Fermi level is passing through the band gap in the spin down channel. But what about the spin up channel? So there are some bands which corresponds to the non-bonding states. So these non-bonding states will have 6 extra electrons. So these 6 extra electrons will give you this extra electrons, non-bonding electrons will give you the magnetic moment in this CO2 MnSi compound. So this is the example of full Heusler alloys. The first one is you have Fe2VAL, and this is 2 into 8 is 16, and this is 5 plus 3 will give you 24. So if you go to the Slater-Pauling rule, this will give you 0. So it should be semiconductor, non-magnetic semiconductor. So if CO2 FeSi will give you the this one, the same as this one. The result will be your 6 extra electrons out here will give you the magnetic moment 6 here. And here, this is a little bit tricky. This is ferromagnet. All these are ferromagnet, but this is Mn2VAl is a little bit tricky because all the see the moments. Okay, the moments of the atoms are not parallel to each other. Some of the moments are anti-parallel to each other, but they could not cancel the moment of their adjacent atoms completely. So that's why this structure is the ferrimagnet. This is the ferromagnet. All the moments are parallel, and this is not the parallel. Some of the atoms are anti-parallel to each other. So you can see this blue, and especially the blue is the moment. The direction of the moment is around along the z-axis, positive z-axis, and this blue is downward. So they cancel each other, but they could not completely cancel each other. So in that case, so the magnetic moment is 2 here. If you directly follow the this thing, it should not be 2. It is something like 18. 18 and 8 will be 26. 26 will give you 2, but here this is not completely this is not completely a ferromagnet. So some of the moments are cancelled to each other. That's why it is coming -2 here. So you can see out here. So this is the 4 and 4 here, and this is your 8 electrons here. But 8 electrons and 6 electrons are not symmetric to each other. So 8 minus 6 will give you 2. 8 minus 6 will give you 2. So here 8 minus 8 will give you 0. 4 minus 4 will give you 0, and 0 and 6 here. No any bands are out here. So 6 electrons will give you completely 6. But here 6 and 8 is completely 6 electrons, and the 8 electrons are antisymmetric to each other. So cancelling each other will give you some value of magnetic moment. But the magnetic orientations or the magnetic configurations of this compound Mn2VAl is very magnetic. Okay, so why this compound is important? Because for magnetic systems or the magnetic technology, I mean the technology based on the magnetic materials, this Heusler compound is also important because it has got some of the important properties like low damping factors, low magnetic moment, high perpendicular anisotropy, and high Curie temperature. So this is our current results. So we work on this Fe2IRSi. So we tested our structure by optimizing the structure. It's a ground state structure, and we found that the ground state or the stable structure is the FMXA. That is, this is the inverse type of. We try with the FM and antiferromagnetic and ferromagnetic coupling, and we try with the and the structure also, the phases also we have changed to because this is the full Heusler type. So we try with the inverse phase also, and we try with the direct phase also. So among the direct phase and the indirect phase, we have found that indirect phase is more stable from this one. This is, you can see the blue dotted line. So it is the lowest. So the inverse structure here is the most stable one. Then we have also tested the thermodynamical stability by calculating the phonon dispersion curve, and we found that all the phonon bands are in the positive quadrant. So we say that this is a stable structure. So, and here we have used two types of functionals. One is GGA, and the one is GGA plus U, because Fe is highly correlated element. So when we treat it with GGA, our result was not that promising, and we have got the magnetic metal behavior. You can see the bands are like passing through the Fermi level from spin up as well as from the spin down bands. So that's why this is the magnetic system. But when we apply the U value, we give the U value for this FED system, FED elements. When you apply the Coulomb repulsion term to each of these iron elements, then we got something different results. So we have found out the band gap out here, and from the band structures also we have found out the band gap in the spin down channel. So we claim this Fe2IR-Si is a half metal ferromagnet compound, and we have also calculated the Curie temperature. So what we have done is we have first calculated the exchange energy. So exchange energy for for this systems, then the exchange energy that we have fitted in these equations to obtain the TC value. This is the mean field approximation result, so formula. So this formula we have found that TC is around 900 K. Okay. And this is our results. We have compared with some of the previous results. CO2 MNSI is 985 K, the Curie temperature, and CO2 FeSi is 1100. I think this is the highest among all the Heusler compounds. And CO2 CRSi is 747, and CO2 FeL that we have calculated, it was found to be 926 to 928 Kelvin. And Fe2COAL 937 and 987 Kelvin. This is by using 937 is by using the GGA, and 987 is by using the GGA plus U. We have found this value of Curie temperature, and this paper we have published in JMCC, Journal of Material Chemistry C. And the result of this Fe2IR-Si, the recent our work, we have found 900 Kelvin. And it is submitted to some journal, and it is under review. And the thermoelectric properties, some of the Heusler alloys are also of very good thermoelectric properties. We know that thermoelectricity is like it's a very noble property that we are looking for to generate some kind of energy to deal with the present energy crisis. So thermoelectricity is one of the the area which we look into, and we can extract some energy for sustainability. So here in thermoelectric, what will happen is if you hit at the one end of a materials and another end of the material is cooled, then there will develop a potential between them. Then there will be a if you connect these two, then you can see this one here, and this is actually a p-type and the n-type thermoelectric materials. And you can see this the p-type, the top of the p-type, and the this n-type is connected with the heat sources. That means it is absorbing the heat. So the materials which will absorb the heat, and the heat will be produced into the electricity. That is the the concept of the thermoelectric materials or the thermoelectric devices. So this is the device which we have seen, this one. So here you can see the higher potential region will be here. So in the p-type, the hole is the carrier, and n-type, the electron is the carrier. So it will move from higher potential to the lower potential. The hole will move from the higher potential to the lower potential, and the electron will also move from the higher potential to the lower potential. So in this junction, there will be excess of holes, and at this junction, at the base or at the bottom point, here at the bottom junction, here will be the excess electron, here will be the excess hole. So excess hole, and this will be positively charged, or you can say this is the positive terminal. So this will become the positive terminal, and this will become the negative terminal. If we connect this one, then we can, the current will flow. So the refrigerating property is just the opposite. When applying the electric field, heat will be generated at one end, and at other end the surface will become cooled. So in this case also, Heusler compounds is one of the contender, because Heusler compounds does not have very high efficiency, but the good thing about the Heusler efficiency is the stability. It has got a very high heat resistant property. That means it can it will not undergo any type of phase transition, even if at a very high temperature. So for high temperature or high range of working temperature, this Heusler alloys is good. So efficiency of the Heusler alloys can be calculated by this formula, S square sigma T by K, where S is the Seebeck coefficient, sigma is the electrical conductivity, T is the temperature, and K is the total thermal conductivity. This total thermal conductivity contains both the contributions from electron as well as the lattice. So in this paper, it has been discussed why the Heusler compounds is a good contender for thermoelectric properties or thermoelectric materials. It is because we have a in this this thing we can see here. This is the phonon bands of the Heusler alloys, and you can see this one, the optical branches and the optical branches. So this is the acoustic branches, and the optical branches are clearly separated. But here you can see the optical branches and acoustic branches are mixing with each other. So this shows that the strong electron phonon coupling. So whenever there is a strong electron coupling, and that will reduce your K. Okay, reduce your K. That means your this part. So if this is small, then ZT, there is a chance that ZT will go high. So efficiency will become high. So another reason is that in the Heusler alloys, what will happen is it has got a flat band near the Fermi energy. So this is the light band here, and this is the heavy band or the flat bands. So here you cannot dope because the doping region is very, very small. Even if you dope out here, so this band will not change much. So this is a flat band. So if it is a it is a thin band. So this low band, the low band will give you the low what do you call this effective masses. So it will definitely increase the electrical conductivity, but the Seebeck coefficient will be low. So Seebeck coefficient will depends upon the flat bands. So here this is more favorable for doping, because you can add more n-type doping here. Here also you can dope more, and if it is if it is doped more, what will happen is it will increase the number of bands near the Fermi level. If the number of bands will increase, if the flat bands are increased, then the Seebeck coefficient will go high. So that is one probability talks in this paper. The another good thing about this paper is that they have also talked about the lowering of the K values. So here, if you dope lighter elements, what will happen is it will not scatter the phonon waves. So phonon waves are less scattered. So if the phonon waves are less scattered, then the value of K will go high. But if you dope here, this is the pink balls. So pink ball is, you can see, compared to this brown ball, the pink ball is scattering the phonon waves more. So more the scattering, so it will act like a barrier of the transfer of the phonon. So that will reduce the K value. So in this and strong, you see this one, heavy elements are there. So heavy elements are definitely good for scattering the phonons. But the another problem with the heavier elements is that sometimes it will the structure will be distorted. So we have to take care of that also as well. So this will reduce the K value. So if we have the higher S and the lower K value, then efficiency might go high. So this is our results that we have published in 2017 here, and this is the volume versus temperature. We have used quantum espresso tool to calculate all these things. And another one is this KL. You cannot directly calculate the KL, that is the lattice part of the thermal conductivity. So we have used some empirical formula called Slag's equation. This scale is given by Cm theta cube V 1/3 e to the power 1/3 that n square gamma square t. Okay, C is the constant for this particular element, compounds, and m is the molecular mass of that unit cell, and theta d is the Debye temperature, and B is the volume of the unit cell, and n is the number of atoms or number of elements in that particular unit cell, and this gamma is the Grunisian parameters, and T is the absolute temperature. So by using this formula, we have calculated this KL, and our results looks more close to the results which has been calculated from the Seng-Bette code. And Seng-Bette is also a very good code for calculating the KL value, but it will the computation expenses is very high particularly in this kind of calculation. So we have used the Slag equations, and our Slag equations result is in more or less comparable with the Seng-Bette's result. So and the electron part of the thermoelectric parameters for this HF-PT-PB Heusler alloys has been calculated by Boltzmann code, which is based on the Boltzmann semi-classical transport equation, and this is the Seebeck coefficients we have calculated as a function of temperature, and this is the conductivity as a function of temperature, electrical conductivity, and this is the thermal conductivity, the electron part of the thermal conductivity, because the thermal conductivity is two part. One is the lattice contribution, and another one is the electrical one. And this is the ZT, the efficiency that we have found out, and you can see that the ZT value, that efficiency is increasing with the increase of the temperature. So we can say this, our system is a very good thermoelectric materials for a higher range of temperature. So higher range of temperature because ZT, the efficiency is increasing. So in conclusions, transition metal-based Heusler alloys exhibit semiconducting metal or half-metallic behaviors that we can pre-assume from the Slater-Pauling rule. So that is one of the advantages to predetermine. Then we can start our calculations, and electronic and magnetic properties can be easily pre-assumed from this Slater-Pauling rule. And meta GGA and DFT plus U is better functionals to study Histler compounds, because when we treated with the GGA, we are not getting up to the result what we are expecting. Sometimes Slater-Pauling rules we can estimate the magnetic moment is 5, but from GGA it is sometimes giving 3 or 2, something like that. But if you use meta GGA or DFT plus U, then you can get around 5, sometimes not exactly 5, but near about 5. Okay, it's a better functional. And half metallic behavior has been extensively studied due to their application in spintronics. So our systems, Heusler compounds, most of the Heusler compounds, transition-based Heusler compounds, are giving the half metallic behavior, and this half metallic behavior is very promising in future technology that is called spintronics. And most of these the Heusler compounds are having high Curie temperatures, so that means it's the magnetic the property will remain intact up to a higher temperature. So that is one of the advantages. And our results of this calculated TC of CO2 FAL, Fe2Cl, and Fe, these are the 3 compounds we have studied till now, and they are also good in agreement with the experimental data. And a half Heusler alloys, that is HF-PT-PV, is a semiconductor, and semiconductor half Heusler is good for thermoelectric properties as well. So these are the references. Jai Hind, and thank you all. And especially, I would like to thank Dr. Dev and Professor Mohan L Verma, who is being a very good mentor for me, as well as a very good friend of mine. Thank you all for listening to me.
Okay, thank you, sir.
Yes, sir.
Any question? Sir, some question in chat box, just like Visakha Singh.
So, any questions? Which software you use for calculating thermoelectric properties? Oh yeah. So for calculating thermoelectric properties, mainly the thermoelectric properties are of two types. One is the electron base. Another one is the lattice base. So for lattice base, we are using Phono 3P or Sengbete also we are using, but those Sengbete and this what do you call this Phono-P are very expensive unless and until you have a very good machine. This is very difficult because it will make a huge number of supercells, and running them one by one is very it's a mammoth task. And for electron part, we are using the bootstrap code. Okay, so in MetaGGA, what we do is like MetaGGA in some code it has been written as MetaGGA, and in Wine2K in our code which we are using from a very long time, MetaGGA is also equivalent to MBJ, modified Baker junction potential. Here in generalized gradient approximations, what you have done is you have only the first order correction has been introduced, but in MetaGGA, the second order correction has also been included in this functional.
Yes,
and
sir.
hyper-GGA, I'm sorry, I cannot, my students has given the answer. I hope you're satisfied, but hyper-GGA, I have not done any work on hyper-GGA, and I have much idea. That is my honest confession.
Okay, any question? Okay. Thank you, sir.
So Mr. Ramesh has asked, since in case of half metal, so see, half metal is generally a kind of metal, no? You cannot calculate the thermoelectric properties for the metals. So in metals, what will happen is your K value will go very high. Okay, so because of that, there is no questions of spin up and spin down. So when you are trying with the thermoelectric materials, basically we are trying with the semiconductors having the low band gap. So if you are dealing with, no doubt the code will give you the results, but that is not promising. I don't think because half metal is also a metal, because like if you see that one of the spin band is always giving you the conducting properties. If it is one of the spin band is conducting, then the this will be your thermal conductivity will go high.
Okay, thank you, sir. Very nice presentation. And
okay, thank you very much, sir. To you also.
Okay, thank you, sir.